Hopefully everybody had a good weekend. Stayed warm, or at least stayed warm last night. We had windows open in our house. It got kind of chilly, but it's that time of year, so it happens. So we're shifting a little bit here to a new topic. We're talking about the growth of algorithms. What you see on the board is, or on the slide, is what's called asymptotic notation. We normally don't call it that. We'll usually say it's big O notation because that's the one that we use the most. We say, okay, what's the worst that can happen is really how we usually analyze algorithms. But the three of them that we have in terms of actual definitions are big O, big omega, and big theta. And this is just kind of an image that was on Creative Commons that talks kind of about what they really mean, bounded above, bounded below, or exactly. We'll talk about what that really means. In your homework assignment for this, what you'll be doing is comparing some values, some test values for different equations. These equations are the ones that we normally use to describe a function. We'll say a function is an n-squared function. Well, what that means is that it's bound by a polynomial on n squared. So, and we'll talk a little bit about why we just call it n squared rather than n squared. 3n squared plus 4n minus 2. Well, the way that we work with this notation is that gives us a bound that we then multiply by a constant. So n squared times some constant will always be more than n squared plus 3, the 3n plus whatever, once you get back past the point. And that's kind of what this graph is showing. What our definition is that we can find some integer value k, a positive integer value, such that our function or the data that we're collecting or the performance of our algorithm will be bound by either have an upper bound, a lower bound, or both by that function. So we'll say it's bound by it, and that's the whole thing that we're trying to do here is determine how things perform. The last little bit in here is looking at the analysis of insertion sort and how we do this. This actually, I'm not sure that this one should have been in Creative Commons, but it was. This comes from a book about this that I can't remember. Corman, Lichisson, and Revest. It's a book on algorithm analysis. Probably the most common book used in most of the world for algorithm analysis. Because it really goes through everything. But this is an algorithm for insertion sort, and it's showing how we do algorithm analysis in general. We'll look at the way an algorithm is written. For example, a for loop, and we'll say, oh, this for loop is done. Well, it starts at 2, goes to n, or the length of that. So 2 to whatever is really can be bound by n. So we'll say it's done n times. And then the thing inside it is actually done n minus 1 times. So we're always going to initialize and start doing stuff, but then we've got a time where we're going to stop. So we've got n here, and we'll finish our for loop. But inside it, everything is done n minus 1 times. And then when we get down here, we've got another loop, and we'll have a summation here of how many times those things are done, and it's based on different conditions and other things. So when you take, we don't usually do too much of this in 2420. It's really just kind of a show you. This is really kind of what the foundation of it is, because it's a data structures class more than it is an algorithm analysis class. But you'll go a little bit more in depth into what that really means in terms of the performance of everything. So that's what we're talking about today. But of course, first we're going to start with a review. We'll talk about what algorithms are, and then we'll talk about growth of functions. The big O, big omega, and big theta, and what those things mean, what the formulas are that represent them. So last time we talked about sequences, or we continued the concept of sequences to being a function from a set of integers to another set, where the values in that sequence are the values that the number 1, 2, 3, or whatever from the set of integers, subset of integers maps to. I'm on the wrong screen here, so my arrow just took me to the wrong place. Okay, so I'm in the right place over there. Now I need to move my mouse. Sorry, the surface here just doesn't work real well with my optical mice. So normally we'll either map from natural numbers of course contain 0, or from the set of positive integers. There are some special sequences. In fact, for your programming assignment, you'll be working with the Fibonacci sequence, and the idea there is that we base our definition on some set of initial terms, and then we use the terms in the sequence to define the other terms or something following it. So it could be based just on the previous one. A lot of times you'll say, well, the nth value is some function of the n minus first value. Fibonacci just happens to use the 2 previous values. There are some that actually use values further back or skip the one immediately prior. It doesn't really matter. They're all recurrence relations in that we're really just saying that a sub n is based on some function of the preceding elements. So if I've got n, it's going to have something in here, like n minus 1 and n minus 10, or something like that, and we'll just deal with it that way. But that makes it a recurrence relation. There are some special sequences, and we use these for our order of growth. N squared, n cubed, n to the 4th. Fibonacci actually grows faster than any polynomial. But then we've got exponentials, which grow faster than Fibonacci, and finally we had n factorial. So these are columns. Go down the first column, go down the second column, and that's kind of the order that they're in. And then for your programming assignment, we also have some special formulas that we use for, or formulae, that we use for representing or for determining the result of that summation without necessarily performing the summation. Sometimes it could be very tedious to say sum all the numbers from 1 to 10,000. You might give your class that as a punishment in elementary school. For like this week, we're going to be summing all the numbers from 1 to 10,000. And of course, if they know the formula, it's pretty quick. So it allows you to do that sort of thing. So what is an algorithm? It's got the word rhythm in it. Well, I guess it's spelled incorrectly. It should have a Y if it's going to be a song. So what is an algorithm? Have you ever used one? For what? What did you use one for?
Multiple homework assignments.
Ooh. Many algorithms have been used. So what did it look like? I mean, because we could represent them a lot of different ways. I could, for example, put an algorithm together for tying shoes. I just picked up some new markers from the other building, and I've got colors. So we could say, for example, 1. We could get as specific as we want. Take each one of the places where the laces cross over the tongue of the shoe and pull them. I'll just say tighten the shoelaces. So we've got that, and then 2. Pull, be loose. ends till tight. 3, cross the loose ends and loop 1 under and between where they cross. What I could go on here, if they actually did it in Shrek, they had, the dragon goes up and around the castle and through the, You guys ever watch Shrek? No?
It's been too long.
And not the original Shrek, but one where they had kids. They were telling the kids how to tie their shoes. So it's an algorithm. Anybody ever cook anything? What do you call the algorithm for cooking something?
Recipe?
A recipe, where you say preheat the oven to 450. Or whatever it happens to be, grease the pan. I just happened to pull up a recipe for oven roasted chicken thighs the other day. So, the first step was preheat the oven to 450 degrees. Pat the chicken until it's dry. But what is that? What does each one of those things do? What are the characteristics of it? I mean, we usually list them something like this, where I've got numbers, or I have bullets, or something. What is this? What would you call each one of these?
A step.
A step. So we're looking at some way of doing or performing some action, of solving a problem. The Air Force Academy, we had a standard definition for algorithm for our cadets. But everybody took the introductory computer science course. We figured technology was important for Air Force people to understand. And we just called it a step-by-step method for solving a problem. And that's really all it is you write out a series of steps with the idea being that at the end of that time, you've accomplished something. How to set up a new, how to set up a new router in your home. How to build a computer. That would be a little bit more complicated than just setting up the router. But things like time shoes, driving directions from point A to point B, go out here to Ed Valson, turn left, go to the first yield sign and turn right. At the stop light there, turn left, remain on that road till you reach something else. But they're driving directions on how to get from here to, for example, the other campus. Turn left on 89, drive on 89 until you reach the 193 exit. Go west on the 193 exit till you reach the first stoplight after Hillfield Road. Turn left, follow the little drive down, and the first building, the building to the farthest east is the C80 building. And then, of course, the recipe. All of those are algorithms. We've done them. We've used them pretty much our whole life, I think. Your parent might tell you, go to the store and get these things. And then we'll write the list of things in the order that they're going to appear in the store. But we can express them in a lot of different ways. English is not always the best way to do it. For example, the English is not precise. I always like Sally gave her dog a bath in a pink t-shirt. So who's got the pink t-shirt on? It's either Sally or the dog. Those are the only two things we're talking about. But English isn't precise. English is not precise enough to really represent a lot of the different things that we do. So instead, we usually find a mathematical notation for it. For for computing, we usually use pseudocode. Pseudocode is based on, it's not really language specific in general, but it's based on common concepts from different languages. How many languages have you used that don't have arrays? Yeah, Python. If you've used Python, you probably have lamented the fact that it's a list, it's not really an array, but you can kind of use a list as an array, or you can use NumPy, which is their mathematical thing that does include arrays in it. So you can add, there are some libraries that allow you to do that. But the idea with pseudocode is that you use that pseudocode, the closeness to a computing language, which is all computer languages are defined using a grammar. We're going to be talking about grammars and languages the last module of the semester. But all computer languages are actually defined by a formal language, which is why the compiler is able to tell you you've broken the rules of the language. And then we get some semantic meaning from that, and you can actually embed semantic meaning within the grammar, and we'll do that kind of thing. But it's more precise than English. We use program-like structures, like we can talk about arrays on the title slide for the course today. We had the algorithm for an insertion sort. Insertion sort's like if you've ever played a game of cards and you pick up your cards one by one and you put them into some kind of order, like group them by suits and then have them be in numerical order within the suits, that would be an insertion sort, where you pick them up one by one and put them where they belong as you're picking them up. That would be an insertion sort. So we had the algorithm for that earlier. The idea usually is that our algorithm or our pseudocode is close to all programming languages. It might be closer to one than, for example, I tend to write most of my pseudocode in C++-like language because most of the students that I have in different classes are familiar with C++, and if I'm doing something old enough, it's actually going to be C, not C++, so I won't have any classes and but I tend to use words like print as opposed to cout, because when you use in Java, you use system.out.print or something like that. But people understand the concept of print. One thing we could do, for example, or is give an example, sum all the elements in a list of n integers. So we can initialize sum to be the first element. So we've kind of taken the concept here that I've got that list of elements. We could do this by, for example, asking somebody, please enter the first number, the second number, the third number, or some other means like that. But then we would ask for the remaining elements, and then we would compute the sum by sum is equal to whatever the sum was before, plus the remaining elements. Now, if I wanted to actually convert this to some language, how would I do that? Really hard. This one especially is really hard. Because I've used something like a for loop. Do you have for loops in any of the languages you use? No, you don't. Actually, you do. So it's pretty easy to do. We could just do sum equal, for example, let's say that we have an array. So array, I don't want to continue my presentation. They've added some features. I need to turn off some of those features. Because I tend to hit the wrong button every now and then. So assume the sequence is in an array. So what language do you want to use? Well, that's where we start getting things. Here, we're just saying a sequence. And usually algorithms, for example, if you look at the insertion sort that we had on the very first, on the cover slide, it assumes that your index starts at 1. What language do you use and what index value does it start at? C++ is probably the language most of you use, and first index is 0, it's not 1. So what we would do then is, understanding the concept here, this is the first element of some sequence, but stored in an array, it's the 0th element of the array, then we would just modify our numbers here to take advantage of that. So some would become the array indexed by 0, and then we would go say for I equal 1 less than n. And so that would be the way that we would do it. In fact, we could even shortcut this a little bit. So let me blow your mind just a second here. Little C++ magic. I'd add in the summation in that part, but I don't have enough room, so instead I'll just do sum plus equal a sub I. Ta-da! In fact, you could do it all with just one for statement by moving this part after this semicolon over on the right-hand side. Right before the I++, just separate them by commas and you're all set. So converting from an algorithm, we have to understand the difference in terms of the way the algorithm is represented, because usually we start with 1 instead of 0, but we also have to understand the capabilities of the language that we're using. I believe C or Java will also allow us to do the same sort of thing. C will as well. Python, because we don't have arrays, we would have to use a list, or we'd have to build an array, another kind of structure to do it. Or use the NumPy library. NumPy library, I guess is how it's really supposed to be pronounced. Algorithms have some properties. The first one is our algorithm needs to have an input and output. Now, just like computers, what are the main components of a computer? I'll get you a leg up on your 2810. What are the main things you have in a computer? 4 components. Usually drawn, let's see how my blue pen works. Usually you draw it like this. Four components of a computer. Well, I've got something that does all the work, something that holds all the data. This is, if you've got a desktop, this is the box. What else do you usually add?
Motherboard.
Well, hopefully that's inside the box.
An input?
An input, yeah. It's always nice to be able to get your computer to tell your computer what you want it to do. Keyboard, mouse, most common. You could also view things like network card and other things. Any port, any input port is an input to the computer. The other thing? Output. Yeah. So I need to have all of those things. What do I have if I'm missing these two? A box that does what? So if I do this, they gave me a defective pen. Oh no, green is the best color for doing this. There we go. It's a space heater. So, this is especially true if you have an older computer that's at like 200 or 300 watts. So it produces enough heat, you can plug it in, leave the keyboard and the monitor off, and you've got a nice little heater in the corner of your room. And if your hands get cold, you can walk over, rub them on the top, and you're feeling pretty good. Yeah, so we need input and output, and our algorithm is telling us that we're going to have varying stuff coming in, but our algorithm is going to be able to manipulate that and have an output in terms of some state or something that we're going to actually produce. Another thing that we need is we need to have definiteness. So I can't have Sally wash the dog in the pink t-shirt because it's not definite enough. If I said, Sally washed the dog while the dog was wearing a pink t-shirt, then that would be definite enough. There's no ambiguity in what I said at that point. And I need to make sure that you understand. If you've ever read a recipe and it uses terminology that you don't understand, like, or actually there are some things that are a little ambiguous, like beating egg yolks until they're semi-stiff. Well, what is semi-stiff? Does that mean I could park a car on top of them, or what? So it's not definite enough, but English allows us to do that. But because we're talking about mathematical properties and the functions that we use to control the computer, we need that definiteness. We also need correctness. Believe it or not, you can write an algorithm that will not produce the correct output. Sometimes we redefine what the correct output might be. For example, you might have an algorithm that simply gives you an approximation. So I'd like to know what the stock market's going to be in 3 months, or what a specific stock will be in 3 months. So you could put in the name of the stock, some things about the particular market sector that it happens to be operating in, its current price, and then have the algorithm chug along for a little bit, and it'll spit out the approximate value will be 20% up, or 300%, or 90% down. So it gives you the ability to do something. Now we're assuming that the answer is correct, but the answer would be, in that case, the answer would be correct only within the accuracy of our algorithm. We even call a lot of our simulations where we have algorithms there. For example, weather, almost anything with weather. Where's the hurricane going to hit? Well, they have this whole range of places where it might hit, and then it could actually move someplace else. So your algorithm is oftentimes not, it's correct in that it gives you, it's not saying that the hurricane's going to hop off the surface of the earth and show up in American Samoa, but it's at least correct in terms of what input was given to it. We also want finiteness. So in other words, at some point we want our algorithm to be able to end. We don't want it to start our algorithm and have it go on forever. So otherwise it doesn't really do us much good, because how many of you have ever had a computer go into an infinite loop? Did you wait for it to finish? Now, obviously not. You're in class today, unless it's still running at home. So finiteness is always a good thing to have. And then the other thing is, and this is really where we start hitting the algorithmic analysis part, we want it to be effective. In other words, we don't want to waste time. If I could do it in 20 seconds, why do I want it to run for 20 hours? 20 hours would be finite, it would stop in 20 hours, but I might want it sooner than that. I've got a couple of image packages I've used to try and clean up old photographs and stuff like that and remove dust. Sometimes they're effective, they actually do modify the picture, but they can take a really long time. So there's a trade-off there. The better job it does, normally the longer it's going to take. But usually, especially with our output, we want an answer within a particular period of time. If you're flying an airplane and you want to know, you want the aircraft to respond to changes in where the nose is pointed in your stick position, you don't want it to take like 2 or 3 seconds to modify the air surfaces in order for something to happen. So we do have a couple of different types of algorithm, and one of them is really, it's almost an algorithmic approach, a way to actually design them. This particular type of algorithm is used usually when we're trying to find an optimal answer. What's the best way to do something, or best way to get somewhere? So at each step, we would look around and say, oh, going that way looks to be the best way. If you've ever been out in the woods, this is normally what happens if you don't have like a compass or something and you're trying to get back to the road. You say, I know the road is south, so at every point you look at where the sun is, you look at the roads around you, or the terrain around you, and you decide, well, I can't climb up this cliff, I don't have climbing gear, it looks like that, it's kind of that direction to the road, so I'm going to go this way and try and see if I can get somewhere else. So at every point, what we would do is make the best step that we can, or the best choice that we can. The idea here is that we choose that best answer in the hopes that if I put all of those best answers together, I'm going to get the best answer overall. Let's see. So this is what's called a greedy algorithm, and there are a lot of places where it can come close to giving us a good answer, but it's not perfect. There are some problems where this works. For example, let's say that you've got let's say that you've got array here, you've got bars of gold, bars of silver, bars of copper. Those are 3 different kinds of metal of 3 different values. And you've got a box to put things in. If all the bars are the same size, how would you fill the box?
Gold first.
Gold first. It's your best choice. It will give you the most value. And then when the gold runs out, you go to the silver and you choose that. At each point, you're taking the thing that will give you the best value by adding it to your solution. In that case, because all of my bars are the same size and my box is one set size, my greedy algorithm will give me the optimal answer. The maximum value that I can put in that box is going to be driven by how much gold I have, how much silver I have, and how much copper I have. There are some important problems, though, where that may not give us the best solution. And this is another one where, in fact, we might have some gold or other things to work with. So let's say this is actually described as the knapsack problem, where rather than looking at physical characteristics, we're looking at weight. So let's say that we have a backpack or a knapsack where I can carry up to 20 pounds in it. Now, after 20 pounds, the stitching may break out or other things will happen and I won't be able to carry more than 20 pounds in it. So it's the maximum weight I can do it. We do this for airplanes, we do it for boats, where we say that what's the most weight you can carry in an aircraft. Have you ever had to run around? Has anybody ever ridden around an airport for a little while on the taxiways while they burn off fuel? You guys have missed that joy. One time I was flying through Japan, and we got on the airplane, and the runway at Nagoya is only 8,000 feet. And we were on a 747, and they put a lot of fuel on, and it was about 90 degrees or so out, and it was a fully loaded flight. So they said, ladies and gentlemen, it was an American pilot, so ladies and gentlemen, we're going to have to run around the airport and burn some fuel so that we can meet takeoff weight. So we rode around for almost an hour while he burned fuel, till we were finally light enough that they would be able to take off in the 8,000 feet and not require 9,000 or 10,000 feet, which would have gotten us into some of the houses around the airport. So there are times where weight is more important than the size of something. So our goal is to put the maximum amount of gold in the backpack. Let's say that there's a 17-pound bar, 2 9-pound bars, and 4 or 5-pound bars, all of gold. So at that point, the greedy algorithm would tell us, take the biggest one and put it in the backpack. So at that point, we maximize, it's what's called maximizing the current choice, or choosing the local max. So what would we do? Which one would give us the most bang for the buck on the first bar? $17, $9, or 5 pounds.
Your bang for your buck on the first bar would be the 17.
The 17, that's the greedy choice. The greedy choice says, I've got these little ones, I want the big one. And so you take the big one, you put it in the backpack, now what?
That's it, that's all you can carry.
That's all I can carry. My greedy algorithm tells me, take the best choice from what I can see. Well, my best choice is to maximize the amount I have in my backpack, which is 17 pounds in my backpack. The problem with that is, we know 2 19s is going to be better than that, or pardon me, 2 9-pounders are going to be better than that, or 4 5-pounders. That will maximize it entirely. We'll end up with the entire 20 pounds that we're able to fit in, and we've got the best choice at that point. So my greedy algorithm just isn't the best solution. Another one would be, for example, if I were to give you an algorithm and say, okay, I need you to go to Salt Lake City, and I want you to do this by always choosing to walk downhill. Where will you end up?
The Great Salt Flats.
The Great Salt Lake, probably, or depending on what's going on between here and there is a quarry between us and them. So you might end up at the bottom of a quarry at that point with no way to go anywhere else. But that would be an algorithm that you would have that would say at each point, well, walk downhill. If you're trying to get down from a mountain and you don't know what way to go, well, you've got down pretty much in every direction, when you're on the top, in every direction. So you start going down and you always try and choose something that way. So greedy algorithms don't always give us the best choice. So there are other things that we can use, but the greedy algorithm is a quick way to design an algorithm that can oftentimes give us a close solution. Like 17 pounds of gold isn't that bad compared to 0. I guess is kind of the way to think about it. There are other possibilities as well. There are some problems that we have where we have no algorithm to solve them. I mentioned this a little bit before. Big dramatic sound. I should actually put a wave or something with it, with a drum or something like that. The halting problem. I mentioned this before. We can write programs to do a lot of different things, and in fact, a compiler is a great program for converting from one language to another. To do that, it has to analyze the language in your code a little bit and figure some things out. The halting problem is described as being able to write a program that will read in another program and determine whether it will halt on all inputs. The problem is, what happens if you give the halting problem to the halting problem? In other words, your program that's supposed to solve that, and you say, okay, does the halting problem program that's supposed to analyze another program and determine whether it stops on all inputs, does it halt on itself? Well, because we're in the realm of math as opposed to strictly computer science, we can actually prove that it can't be done. You can't write a program that will determine whether it in and of itself will halt. So if you were to assume that you could, you would find out that it leads to a contradiction. And we'll talk about that a little bit more and when we get to finite state machines in our last module. Our last module is actually pretty big. It's topics that are normally covered later on. In particular, our last module is kind of an overview of what you'll look at, of many of the things you'll look at in 4110. But here, the idea is that we can prove that we can't solve some things with a computer. It's always nice to know your limitations, and we have them. With a computer, you can't do just anything. So let's move now into the area of growth. How many of you were over, well, let's see. This might be getting too personal here. Since I've got children, I'll talk about my children. So by the time they were all, well, for both my sons, by the time they were 12, they were both 5 feet tall. I, unfortunately, was not quite the same. I remember playing 6th grade basketball, and by the time 7th grade started, I was still about this tall, and everybody else was about this tall, so it was like, not going to work for me. So I didn't play basketball or organized basketball after 6th grade. But things grow at different rates. And that's really the idea that we're talking about here. And we're talking about in terms of some measure of the size of a problem. So how do you measure the size of a problem?
How many inputs?
Usually how many inputs? Like I'm sorting. How many numbers am I sorting? I'm trying to I'm trying to do some data mining. How many data items do I have that I have to comb through in order to figure out the information that I'm trying to get? So the number of items, I have to have some number of items or some measure of the thing that I'm looking at. As an example, if I'm sorting 2 items, so I've got 2 of them, how long will it take? So I'm going to sort these by the name of the color that they are. So the first one's going to be green, blue, done. What if I had 4 of these? A little bit longer, green, and mix them up so that it's harder to sort. Black ones fell. Okay, which one comes first? Black, blue, green, purple. So not too long to do that, but it's longer than doing two, obviously. But the question is going to become, how many machine operations am I going to perform? Because we're trying to understand how does this affect the performance of our computer programs. If I'm drawing, if for example, I'm trying to draw a screen, if I've got a 480 by 640 screen, old school, that was the VGA resolution. So how many elements did I have? We'll WAG it. You know, you guys know what WAG is? It's a technical term. Nobody in here was in the military, that's for sure. Technical term. It is a term that engineers use. It's a wild guess. So essentially, we're saying, okay, I've got 640 by 480, 480 screen. How many pixels am I going to have? Well, I'm going to have 640 times 480. That's about 600 times 400. So I've got 0, 0, 0, 0, 4, 2. I've got something over 240,000. Not too bad. We can do that. How many do I have if I've got a Anybody have a screen that displays this? Yeah, probably most of you. This is HD. Not 2K, not 4K, it's just HD. We can do that, no problem. Well, now I've got, let's see, I can put three zeros after that, so it's probably about 2,000,000. Now I've got 2 million, so I've got 10 times as many of them. And then if I do 4K, I'm going to have 3840 by 2160. Wow, that's going to be approximately 8 million. So we can look at how quickly things go. But to draw this, let's say that I've got 5 operations per pixel. How many operations do I need? A lot. I've got over 1 million operations for that. If I do the same thing down here, I've now got 40 million operations. So the question is, how quickly do things grow? And do they depend on the number of pixels that I'm drawing? So one of the things that we have with sorting is the number of operations that I have to perform are based on the number of items that I have. With a screen, it's not too bad. I've got a fixed size. But with sorting, I could have a variable size. I could have 5 things. I could have 5 million. And there's a big difference in terms of the performance at that point. If I gave you 100 or 1,000 of them, well, or 1 million. In fact, in 2420, I have my students do 1 million integers. They can do less if they can show a difference in the performance between some of their algorithms. The reason we're concerned is that if I'm sorting, for example, sorting is based on, for comparison sort, sorting is based on the best performance, which would be n log n. I can't do better than n, 1 million items, times the log of n. So as n grows and the log grows as well, so I'm getting bigger and bigger and bigger, and it takes longer. But most of you have probably done things like bubble sort and insertion sort. Those are comparison algorithms, and they take n squared, not n log n. So as a result, I'm now talking about, well, what's a million squared? What's a quadrillion between friends? So at that point, or actually I guess that'd only be a trillion, or that's a billion items there. But if I had a million items, that'd be a trillion item, or a trillion operations would be the foundational number that I would then apply for my computation. So when it comes to growth of functions, what we're concerned with is which one of these tells us the performance characteristics of our problem. As a problem grows in size, the time to solve it usually grows as well. There are some things, for example, that might just be order 1, so it's always constant. So never worse than a constant factor. So the algorithm that we use is going to be the thing to do. For example, if I were to choose simply the first thing to come along, that would always be order 1. I just have to wait for the thing to come along, and then my algorithm just takes, I've got it. You gave me something, I've got it. If you give me a million more, it doesn't matter. I can take the first one and I'm done. But sorting doesn't work that way, and most algorithms don't. When it comes to bounding this, we use what's called big O notation. Big O gives us the ability to describe the time for a function based on, or time for an algorithm based on some function. To say that if I measure my problem in terms of how many inputs there are, then I can bound it by how many inputs there are, a function of how many inputs there are. So our formal definition for big O is this. If I have a function f of x that could be measured in terms of, for example, if I have 10 items, I would measure the time. If I have 100, I would measure the time. So my function could be determined by simply running it on a computer. That would be my f of x. And a function g of x from the set of integers to the set of real numbers. Then the big O notation is saying that the size of the f of x function, where f of x would be the time for my computer program to finish, is bound by this other function multiplied by some constant. So the constant is what gives us the ability to say, for example, with polynomial functions, that, well, once you get past some value here, I don't have to worry about the x term if I'm using x squared, because it's going to be smaller. So, as an example here, let's say that f of x is equal to x squared plus 10x plus 23. Well, the question is, what if g of x is equal to x squared? We know that since f of x is x squared plus 10x plus 23, that's always going to be bigger than x squared. However, the question is there a point where I can multiply this by something and I can just ignore this part? So, and usually you do this by selecting k and then you choose your c. So let's assume, or we'll choose k. Give me a number, any number, well, positive integer. 20. Oh, K is 20. So I want something where 20 squared is greater than or equal to hang on. So I've got at 20 squared, say 20 squared is equal to 20 squared plus 200 plus 23. So I've got to get something that when multiplied by, this is 400, this is 400, something that when multiplied by 400 is going to be greater than 623. Why don't I choose 2? C times that, greater than or equal to that. So we'll choose C equal to 2. And at that point, what happens, for example, for 21? Okay, so for x equal 21, we've got 21 squared on this side. What we want to know is 2 times 21 greater than or equal to 2, pardon me, not 2, 21 squared plus 10 times 21 plus 23. Plus 23. So we can pull out our handy dandy calculator and we can try it. Programmer one, I want the problem. So I want the sign, let me have the scientific. And we'll say, okay, I've got 21 squared and 441. So that's going to be 441 times 2, which will be 882. Is that greater than or equal to 441 plus 210 plus 23? That'll be 674. So yes, 882 is greater than 674, so it holds. And what you'll notice is this is actually going to grow faster than this at every step. So as we keep going, this is always going to be bigger than the thing on the right-hand side. So if I multiply 2 times x squared, once k is bigger than 10, or once x is bigger than 20, pardon me, then it will always be bigger than 2x, or x squared plus 10x plus 23. So at that point, we can say, well, x squared is an upper bound for this. It will never be worse than x squared, where c is 2. Now, we might find a c that would be a little bit tighter, but the point is how quickly it's growing, not an exact value for our constant. So why do we use this? We use it because we want a bound. And we can use it for size. For example, if my size is growing based on the number of elements that I have, or my program is growing in terms of time based on the number of elements that I have, then I have to have some way of saying, well, can I solve this for whatever number I have? One of the areas where this really comes into play quite a bit is weather. How accurate can our weather be? Well, it could probably be a lot more accurate than we currently have it. But the problem is that to do that, our algorithms, the algorithms that we currently have require enough data, enough N data, that the time grows enough that for me to accurately predict tomorrow's weather takes more than 24 hours. So what we do is we decide, well, I don't really want the really, really accurate model. Give me a good enough model that takes less time, and I can give you an estimate. You know, yeah, it's going to be warmer tomorrow. It'll be 60. And we use that as a means of determining how am I going to solve this problem? When do I need a result? How can I actually make things work? We use the set functions to compare the growth, and those set functions are really determined just by the functions that you've already seen. Usually we start with log n, or actually we start with a constant. If I have, for example, my function f of x is equal to 3, and g of x could be a constant as well. 3.1 will always be greater than 3. So I have that, and I say that it's simply a constant times the function where f of x is equal to 1. Because the constant c will take into account that f of x is actually equal to 3, we can say that it's order 1. It would be the declaration for that. So g of x would be the function that we're looking at. We may look at something other than just how fast something grows, the upper bound. We might, for example, want to say, well, how good can I actually get? There are some algorithms that for certain inputs, we actually have a really, really fast thing. For example, bubble sort. Have you ever tried a bubble sort algorithm on a list of elements that's already sorted? It's order n. You only have to go through the list one time and you're done. So that's really, really nice. It's a way you can tell whether or not the list is in order. That's really all that you're doing, if it's already a sorted list. But what that means is that we have reached a point where we can say with certainty that our best case is going to be order n for a bubble sort. So as a result, we may want an upper bound. We might say, well, bubble sort performs poorly most of the time, but how well can it perform? What's the best it can do? And in that case, for a lower bound, we use big omega. And instead of saying that f of x is less than or equal to c times some function, we now say, well, is there some k, once again, where we can find a constant multiplied by our other function such that f of x is always bigger than that? So for bubble sort, once again, what we find is that it's an n squared algorithm for an upper bound, but it's an order n algorithm for a lower bound. So it's always going to be somewhere between those two, depending on the input that we have. So it provides us with a lower bound or an order big O. So, or pardon me, big omega. So big O is really saying that if I've got this function, that if this is f of x, that means that I can find another function that as n gets bigger and bigger and bigger, this is really talking about the And this is where the asymptotic notation comes in. We're talking about as n gets bigger without bounds. So this means that as n goes to infinity, if I could do an infinite number of items with my algorithm, can I bound it? Or does it grow uncontrollably? So in this case, what we're saying is, well, maybe we have this function here, g of x, that's always, actually, that after we reach some value, it's always going to be greater than that. So we find some k and we do that. For our big O, or pardon me, big omega, we're actually looking at the other side of that. We're going to say, okay, I've got this function, and let's say this is f of x. The question is there some formula that I can come up with over here such that once I get past a particular point, wrong one. Well, maybe my k is out here somewhere, and I say, well, this is my g of x here. Once I get past that point, f always takes more, or it never gets better than this, would be kind of really the other way to look at it. I can never get better than that. And then our final thing, if they're the same, then we say that we have a tight bound on it. It's a theta, big theta notation, and we're saying that given the same function, I can have a C1 that gives me a lower bound and a C2 that gives me an upper bound, or they are linear, it's linearly bound by that function. In other words, that constant is just a constant. It's like 1 and 2, or 1.03 and 1.05, something like that, times that function will bind the performance of my other algorithm going forward. That's all I had on there. And really, if we were to draw this, I thought I had more on that. So if I had, oops, let me change colors here. So if this is g of x, and this is g of x, and this is C1 times g of x and C2 times g of x, or actually, I guess normally we're going to have this be C2, and this would be C1 now. I knew I was going to get my g. So C1 g of x, then we can say C2 could be equal to like 3, C1 could be equal to, let's say, 1.5 or something like that. And we're saying that, yeah, this thing's always twice as big, but we're always going to be between these two. And I might have some oscillation in the function or something else, but it's always going to be between those two. So I have a tight bound at that point. That is when we say that a function. So we have some terminology that you'll hear. There is order. We usually reserve the word order For big O, and a lot of times we'll say bound by g of x if it's theta g of x. And then for big omega, which is probably the least used of the three, big omega is simply a way of saying it's the best that you can do. So well, we'll just usually call that big omega. I've never really heard a term. But usually we'll say that it's order whatever, or like bubble sorts order n squared. As an example, bubble sort because it's big O, but it's not beta n squared. And that's because big omega is omega n for bubble sort. So what that means is that the best case is some function of n. So if I've got 25 items, it might be n, 3n. So it'd be order n. But if I've got 100, the worst case, if I've got n, could be 27n squared. But the constant is just one that we choose in conjunction with the value k. It says for every value of k bigger than some set value. And I guess that's one other thing I forgot to put here is A is the maximum of the k for the big O and the k for big omega. So we can choose the C1 and C2 based on big O and big omega. So C1 comes from the big omega, C2 comes from big O. So this is from big omega, and this one's from big O. And that gives us our big theta. So most of the sorting algorithms are usually the ones that we use to talk about this the most because it's easy to see. And we have a lot of example data. You can generate it pretty easily. And we've got a bunch of sorting algorithms. What's the best you can do with a sorting algorithm? Anybody know? Actually, a lot of it depends on a description of the algorithm. If I have a comparison sort, then we're looking at order n log n. Actually, it's theta n log n. For compare, actually not theta, because bubble sort is also comparison sort. It's omega, big omega. What that means is if my sort is based on the idea that I compare this value with other values in the list to determine whether or not it's in order, then it's never going to be better than n log n. So n log n is the best I can do because I have to compare it with the other items in the list. For non-comparison sorts, we actually have, there are a couple of sorts that are order n, not order n, yeah, order n. One of them is called a bucket sort, where the problem with most sorts that actually do better than comparison sorts is that they take a lot of room. So The one I always think of, I'm trying to remember the name of it now, and I probably won't remember it until I start looking at my 2420 notes before that class, is essentially you build an array of all the possible values you could have, and when you get that value, you put it in order. And then you also have a value in the array that tells you there's nothing there. So you only look for filled elements in the array. But what that means is, for example, if I'm sorting integers, how many elements do I have? If I'm sorting signed integers, how many elements do I have to have in my array? Even if I'm only doing the positives. 32-bit integer, signed, that means that it's 2 to the 31st roughly. So it's roughly 2 billion. I have to have 2 billion things in my array to sort. So I have to have an array that can hold 2 billion if I'm sorting 100 numbers. So the time is order n. The space, a lot bigger than that. So it's got a really huge constant is what it boils down to. All right, we've got a few minutes left. Questions, programming assignments, homework assignment. Everything's clear as mud, don't have to worry about it. You're going to have the programs done. In fact, you've already finished all the ones through the end of the semester and you're just waiting for me to get there.
Man, I wish.
I did have somebody during the summer. I taught this online during the summer and I had somebody who finished in about 5 weeks. She was, I think she got the top grade in the class too. She wanted to finish it so that she could take a flex class. Summertime, if you're not taking more than like 2 or 3 classes, then it makes it a little bit easier.
Hey, Dr. Rich.
Yes?
Could I get help with the program?
Sure, that's what this time is for. So what's going on?
I think it would be easiest if I just show you the code.
That probably will work best. Okay. And this is the, manipulating this, okay.
This is program 3.
Right. So what are we doing? What are you you're trying to print out this set?
Last time I talked to you, you said I needed to use some functions, so I made functions for it, but I also made another function to print it out later.
Yeah.
That function never worked.
So well, let's take a look at it. Let's take a look at it, because having a function that prints it is probably the best way to do it. So let's go up to the function that you had, not the code, not where you called it, but where the code is.
Okay, sorry, I'm just going to comment this out so that it doesn't interfere.
Yeah, because you will want to use print set for every one of the ones that you're doing. Oh, you're including a set name. Okay. I don't recommend doing that.
With the set name?
Yeah, because you can label it before you call print set, and then that way print set is focused on just printing the set. You have a line before you call print set that says, the set A equal, in my main program here, give me a second. Let's see. I I would have, in my main program, I'd have something like cout, and I'd just say, before I print set A, equals space, and then I'd call print set with the variable set A, and that would print. My output here, what I want is set A equal parentheses, curly brace, like 1, 3, 7. If those are the elements that are in the set. That's what I want to see. And the way to do that would be, and then a cout down here with an end line. So the way to do that is I need a function. I guess you guys have probably been taught to use camel case, so I'll use camel case. So in here, I'll have int, be set. So I need a loop variable. And then I want to start at 0. So, well, first I want to have, you see I didn't print the curly brace there, so I need to print the curly brace and the curly brace at the end. And then inside, if bit I is set, then what I'm going to do is print I. And then if a number has already been printed, then I want to print a comma space before I print the next one. Does that make sense?
I think so.
Okay. So I'll have a Boolean. Something that says, I need a comma, and I'm going to initialize it. Do I need a comma before the 1? Or before the first number? Because 1, it could be 0, it could be whatever. I'm going to say...
no, you don't need a comma
I don't.
before it.
So then I'll have a for I equals 0, I is less than, or equal to 9. I'm going to write it that way because the values in our set are between 0 and 9. Oh, I forgot my cout here. Cout, curly brace. So I print my curly brace and then I start my for loop. Inside here, all I need to do is check to see if bitwise and with with 1 shifted left by I, and this will be since you're doing C++, we can do it without the check. The other way to do it would be in Java. In Java, I need to do be set handed with 1 shifted left by I is equal, or not equal 0. So, since we're not doing Java, I don't need to do that, but I've got that in the documentation. In Java, we would have set handed with 1 shifted by I. Or we could do not equal or greater than equal to 1 work. But then inside here, all I have to do is if need comma, then I'm going to print the comma, cout, a comma and a space, and all that is for pretty printing. Pretty is for pretty printing. The only other things I do, I would do a cout I, because if the bit is set, that means that number is in my set. And then I would need to set need comma equal true. So the first time through here, whatever the first number is does not have a comma space in front of it. Every other one does. So that is the end of my if here, and then I've got the end of my for loop. And then down here I would have cout, and I put my closing curly brace. And that is all I want my function to do. I just want it to print. The only thing I want print set to do is this part. I don't want it to do anything other than print the set. If I want to label it with something or anything else, I can do that elsewhere. But here, I just want it to print the set. Okay, so let's see where we're at here. I'm assuming you're reading in the values okay?
Yeah, when I read that, it's all fine right here. This is okay. It sets the bits to be the right bits. But the problem is that when I call print set, it only ends up printing empty.
Yeah, you don't need number of elements. You don't need element. You don't declare variables there. So all you need is the set. And that appears to be what you're calling it. Probably not a good thing. On line 10, you're calling it set, S-E-T.
Yeah.
I don't know why you're doing using number of elements in there. That is nothing.
I'm just using number of elements so that if
No, don't pass.
greater than 1, it'll put a comma.
No. Please don't do that. Use a Boolean. That's what they're for. And don't pass it in as a parameter. Wait, so what are you doing here? For int I equals 0, I less than 10. And then you're not changing I. Oh, yes, you are. You're changing. Okay. You're not following the convention with for loops in that you increment inside the loop for statement itself. This function should only take,
Right here in increments.
no, I know that, I'm talking, that should be in line 7, because it's a for loop. If you don't want to increment in line 7, you should be using a while loop.
I was experimenting with something else last time.
But for line 5, the only parameter you should be passing is the integer value that contains the set. Nothing else. It doesn't, you don't need all that other stuff in there. It has nothing to do with printing. And num elements is not a good name for your set.
No, I just call set. The set.
No, I understand. But okay, then num elements is not a parameter. It should be a local variable if you're only using it to control whether or not the comma space is printed.
Okay, so then I shouldn't even have this anymore.
That is correct. You should only have whatever parameter name you're giving the set that is being printed. Because you're not printing anything else. You shouldn't have to give it anything else if you're printing. Everything else should be a local variable. If you need anything else in your program, a local variable. Don't tie, but otherwise what you're doing is you're tying threads in your code where you've got things that depend on something else, and that usually leads to really major problems in your code. So that becomes, the num elements there becomes a local variable. And you saw, if you look at my code, I declare it Boolean. You can use an int if you want.
Okay, so for bool, could I just put like...
The name of the Boolean could go there. Yeah, if you look at the string or the function I wrote, I used need, comma. NEEDCOMMA. Because that's what it's telling you. It's something that's telling you, I need a comma here.
Okay. Oh, would this work just fine?
No.
I was unable to get the part.
You need to declare the variable up at the top so that you can check it.
If it is not valid, then that was simple, but valid.
You have to have a way of telling, did I print something yet or not? That's what what the need comma tells you. Need comma tells me, do I need to print a comma and a space before I print out the element of the set? That is
So I need to
false.
create another if statement?
Pardon me?
So I need another if statement for this?
To control when the comma space is printed, yes. You just erased it. And you probably want to move it before printing out I.
This is valid and this is not valid.
Can you see my screen at all?
I can, it just doesn't make sense to me.
Okay. You're changing it to match what I just did, essentially. So inside here, the only thing that you're missing are a couple of different things. Inside, right after the cout for I on line 17, the end is in line 17. End of line 17. Press enter. And now we need to say need comma is equal to true, because the next time we print something, we want a comma space. The first time, we don't.
So you usually
So then,
Yeah,
this,
today or you just go
no, don't declare it there. Then its scope is only inside that if statement. Declare it at the top of the function.
Yes.
I suggest that you avoid any inline declarations, like the for loop where you declare the integer I. Old school practice was you declared all of your variables at the top of a function. I realize that they try and tell people to declare them near where they're used, but if you've got hundreds of lines, you want to declare everything at the top. And then where you declare need, comma, initialize it to false.
Okay.
What that does is it says, for the very first number where the bit is set, I do not need a comma space. I need a comma space for the rest of them. You've got one more thing to add, and that is before your for loop, you need to have an opening curly brace.
Oh, okay.
That's
I
C out.
wrote it down here.
Oh, no, that's, don't print part of the set elsewhere. Your print set should print the set. And the curly brace is part of it. I know, the label is fine. It's the curly brace. There you go. And now just move the curly brace up to right before the for loop. You print the curly brace. And the other thing is that adding the new line on line 22, you should not depend on that especially if you're using somebody else's code. You should control new lines in your main program where you're labeling things and everything else. So what we should do in print set is exactly the minimum of printing a set. A curly brace, the elements in the set, and then a closed curly brace. That's all we want it to do.
Okay.
That looks like it should go.
I'm running it.
Okay, so we're getting nothing there. So hang on, let's take a quick look at, okay, read set. Your problem is that in read set, which also has a bunch of things that should be parameters declared in there, you should return the set. And you're not doing that. So I would declare the set as a local variable inside there, initialize it to 0, which you don't do. But you need it to be 0. You really don't need any of the other stuff, the element num or anything else. Those should all be local variables. Don't pass parameters if they're only used if you're using them inside a function. You should, unless you need a value and need an actual value, you shouldn't have a parameter.
This here, like,
If you
just
want to leave that in,
is
that's
that-
fine. It
with
complicates
an
your
element of just the amount of elements.
yeah, it complicates your code a little bit. And for me, I would have read set just do that. Read a set, ask how many elements are in it, and then read in the value. That would be the only thing that it would do. Element is a local variable, so it should not be a parameter. And I don't know what you're using element num for. Well, element num. Okay,
Number of
that's the number of
elements.
elements. Yeah, that should be a local variable too. Those should both be local variables because you read them in here, you use them in here, and then when in your main program, you couldn't care less what somebody put in there because it changed inside the, well actually here, these are local variables masquerading as parameters. Element. Yeah. You need the string because you're going to prompt them, I want set, whatever. And that's the only parameter you need coming in. You need to change the return type to int from void. And then down in your main program, that will just change your call. Shouldn't change anything else. If you've been reading them in properly, it shouldn't change anything else. In your main program, all you will do is when you call read set, you'll say set A equal read set, and then in parentheses the A as a string. It'll be set A space equal read set parentheses set A, and then the same thing for B. So on lines 67 and 68, you need to store the value that comes back from the function. So before read set on 67, put in set A equal. Space equal, and then delete, press the delete key. Press delete, there you go. And then do the same thing for B, set B. Yeah. Because read set is returning the integer that contains the set number, the set elements, the bits. Because you have the return down at the bottom of the function. So it's returning an integer, and as long as that integer has the values, then they'll be put into the set. So that should solve the problem where the sets didn't have anything in them.
And then, should it allow for duplicates?
It doesn't matter. If I set bit 3 to a 1, and I then set bit 3 to a 1 again, it's just that one bit, so there are no duplicates.
So it doesn't show the second two?
Well, no, like I said, it's only one bit, and the set cannot have duplicate elements.
Okay, because I just looked at one of the test cases and it had one where it was like duplicates, so I thought that was the output.
No, the test cases that I list there are all the input test cases that I'm going to use.
Yeah, one is 3, 4, 5, 3 for set A, which has 2 3s. So I thought that it should have allowed for duplicates or something.
Nope. You can only set the bit one time. You can't store multiple values in there, in a bit. They're only 0 and 1.
Okay. I guess now I just need to do the unions and other complements.
Yep. And And if you look at some of the lecture videos, you'll find that they're all you have to do is print a label, and then you have a call to print set with an expression inside of it. You guys are coming in early.
Freak me out.
I have to talk to the mayor. Say, hey, you're letting class out early. First time I let my class out early. I guess I shouldn't say anything after all.
And then with this, do I just type in like set A and then I would use the bitwise operator for that?
Well, you'll need a print set, and then the expression inside the print set can be, it doesn't have to be a variable, it can be an expression.
Sorry, what was it?
The next line would be a call to print set with the expression for complement of set A inside there. Complement is the tilde, set A.
Oh, that's not filled in. Okay.
Yeah, I can't quite make out the characters you're typing. The tilde is normally up to the left of the 1.
Yeah, I got it. I accidentally put a single quote or something.
Oh, okay.
Okay, so and then that's how I would do it for the rest of them.
Yeah, you just put the appropriate expression in there.